Good morning, and thank you for joining us for another session of this 5 days FDP titled Infrastructure Development, sponsored by All India Council for Technical Education under ATAL scheme and organized by Civil Engineering Department, Government Engineering College, Bilaspur. A little housekeeping before we get started. All participants are requested to ensure that they enter their full name while joining the session in Microsoft Teams. Because their attendance and certificate is going to be marked and issued on that basis only. Our exam will be conducted at the end of the session last day, which is of objective nature. Detail will be shared later. And last day we got a lot of support on your behalf regarding the mic issue and all that. So we expect to continue that support today also. So now without further ado, let's start the session. The topic for this session is Telecom Infrastructure, presented by Dr. Ajay Singh Raghuwanshi, Professor, Electronics and Communication Engineering, National Institute of Technology, Raipur. He received his BTech degree in Electronics and Communication Engineering from the Northeastern Regional Institute of Science and Technology in the year 1993. Later, he taught in the College of Science and Technology, Phuntsling, Bhutan till 2007. In the year 2012, he received his PhD from Motilal Nehru National Institute of Technology, Allahabad. During 2010, professor in Indian Institute of Information Technology, Allahabad. Later on, he joined NIT Raipur as an assistant professor in the year 2015, and at present he is working at the same place. Till date, he has more than 30 SCI and Scopus Index research publications in different journals. His research interests are in the area of artificial intelligence and machine learning, best approach in data aggregation and intrusion detection in wireless sensor network and Internet of Things. Sir, we are truly thankful to you for joining us for today's session. We extend a warm welcome to you and request you to start the session.
Thank you. Thank you very much. Good morning, participants. Good morning, sir.
Good morning.
And all the participants. So without taking any more time, I'll just start with my presentation, which is already on the screen. And my first slide might be already visible. So I'll start with today's presentation, where we'll see how our country has come up with the telecom infrastructure from almost nothing before this century, and then we have quite a good infrastructure right now, and we are moving quite forward. So, this is was my first slide. That is so the telecom infrastructure, present, past, and future, and now. So the content that I'm going to take, because I've been told that most of the participants are not from electronics background, so I've not made my presentation very technical. It is more of informative than technical. So we will first we'll try to understand telecommunication. Then we'll see what exactly accounts for this infrastructure. Then we'll have a historical perspective of Indian telecom. Then important telecom infrastructures that are currently needed for any country. Then the present state of telecom infrastructure, that is our own country's present state, how it is, and then future of telecom infrastructure. So this is how my content is streamlined. So going into the first slide is communication system. So first of all, we should have an understanding of what exactly is communication. So when it comes to communication, so communication is basically what we can say is information exchange. So when we say when communication starts, actually the communication starts with the first cry of any newborn baby. So the day mankind would have come on this earth and the first baby might have cried, that was the first communication that might have taken place, because the cry of baby gives you a lot of information. The information it gives you that it is life, it is healthy, it is breathing, it is able to breathe in the air. And so the first cry of a baby, it gives to the doctor or to the nurse as well as the mother the assurance that kid is living. So communication is basically the information that needs to go from source to sink. So when it comes for telecommunication or say electronic communication, it is the electronic medium. That is, we use electronics, and for very long distance, when we are able to communicate the information from source to information sink. Source and sink, they essentially are human beings, and the information could be, if it is say sound, then it is audio signal. If it is vision, it's a video signal, and so on. So the first thing that, so we need to first process the information. So information need to be coded. So the first thing we use is a source code. The basic use of source code is to make the information in a manner that when it travels further, it doesn't consume so much of bandwidth and so much of, so source code is more to do with the conservation of bandwidth and other things. Then after that, we have a channel coder. Channel coder is basically to make the information secure, so that when it goes onto the channel, we have distortions, we have noise. So, and there's a lot of distance between transmitter and receiver. When we are saying about communication systems, the main problem is the distance, because the distance, it can be countrywide, it can be global. You can have information source in one country and sync maybe somewhere else. So we need some technique to change our source information and be modulated. We basically use a carrier for putting the information onto the carrier, and then we use a converter, that is your digital to analog, because most of the time now transmitters, if you see this box, this is a transmitter. Nowadays, all the transmitters are digital transmitters, but transmission is still analog. So digital to analog conversion is done here, and we get the symbols. And this symbol through an antenna is transmitted. If it is wireless, it is transmitted. It can be optical fiber, channel can be optical fiber, it can be wireless, it can be married, it can be anything. So the signal travels on the channel, then reaches to the destination through the channel. This is the channel which determines the infrastructure. So this channel can be wireless, can be wired. So we'll see all those things in coming slides. And there we have to protect the information from distortion and noise, which is external to the channel. Then we get back our signal. Once we get back the signal, we demodulate it to bring back the signal into the form in which it was transmitted. Then we decode the channel encoder. So channel decoder and encoder, they has to be similar. Then we have a source decoder, and then the information reaches back to the destination. So this is the entire communication scenario. So any communication, irrespective of what kind of communication we have this, the entire scenario is similar to this. So the three things which are important here is transmitter, receiver, and the channel. So communication infrastructure actually means kind of transmitter, kind of receiver, and kind of channel. And the rest is there. So what we can say is communication infrastructure gives us the way to transfer information from source to the sink. So this is what communication infrastructure does. So these are some examples of telecommunication. Now telecommunication, basically tele is a Latin word which means long distance, and communication is communication. So telecommunication is a long distance communication. So we call it as telecommunication. Then some of the examples for telecommunications, our oldest example that was used was telegraph. that was used in 18th century and beginning of 19th century. It was one of the most used long distance communication, telegraph, tar. Then came telephones. Telephones is still used, but only their shapes, sizes, and the looks have changed. But telephone happens to be the most used human communication. Now we call them cell phones, so that's why it is there. So, but that is still a telephone only, the long distance audio. So telephone, long distance audio is the telephone. Then long distance vision is television, which is still there. And only the way it was black and white, then came colored, then digital, now all digital, and so many other things. Then we have cell phones. Cell phones, we can say this has this is the main change that has happened, which has made communication global. And being the size and other things have gone so small that each one of us is now moves with a smartphone. And smartphone is, you can say, they are computer by themselves. Most of the smartphones that we use have much better capabilities than the old computers that we had. So the cell phones. Then we have satellite phones. These are also kind of cell phone, but very limited to the satellite communication. Then for long haul communication, nowadays the present scenario is optical fiber communication. We'll talk about it. Then we have data communication networks, which provide us all this information onto the networks. And the most modern way of communicating right now is internet. So which is where you can communicate all kind of information, including now even the market is on the internet. So almost everything is coming over onto the internet. So these are some of the examples for telecommunication. So we move further and we understand the telecommunication infrastructure. So what exactly is telecommunication infrastructure? So telecommunication infrastructure is the physical medium through which the signals and data traffic flows. So this is a technical definition for telecommunication infrastructure. It is responsible for transmitting bit stream over the physical medium called channel. So this channel, it could be wireless, it could be wired, it could be optical, it could be submarine, or any kind of channel. So over which telecom infrastructure is basically the physical medium through which all signals and data traffic flows. Then what exactly it defines? It defines the electrical, timing, and their interface by which the information sent as signal over the channel. So all the characteristics, the electrical characteristics, the timing characteristics, and the interfacing characteristics are determined by the telecommunication infrastructure. And we can say that it is the foundation of entire communication network. So it is the foundation on which the entire communication network is built. So infrastructure is the foundation over which the entire communication network is built. So examples for infrastructures are telephone wires, which are old. Nowadays, most of the telephone wires are being replaced by WLL, wireless. Then we have telephone cables that were also telephone cables were used even in the 19th century, that is around 1870s. These cables were very much used, and they were used till 60s. But now, most of it is only optical fibers are being used. Now in optical fiber, we have two kinds of optical fiber. One is submarine cable. India has set up first submarine cable link very recently in 2018 only, and that is between Chennai and Andaman and Nicobar. So we'll be talking about that little later. Then we have for long haul communication, we have satellite links or the satellite communication. So we'll see what is how our satellite communication developed in India. Then satellite communication normally for linking use microwave links. So we will see that. And in modern communication, everybody wants a wireless access. So we'll be talking about the mobile technology that is being used. We have first generation 2G, 3G, 4G, 5G. And especially with most of the people, they have a lot of confusion about these 1G, 2G, 3G, 4G, 5G. And actually there is a 6G is also there. So we'll talk about all these things little later towards the end of our talk. So we'll talk about the access networks, 1G, 2G, 3G, and so on. So we start with the telecommunication technology developments. That is how the technology developed from last century till today. So this is just a complete technological overview. So first long distance communication which was used was telegraph. And the telegraph was used using Morse code. And that was from 1845 when it was discovered, and then till 1847 when most of the world was, we can say, the British, they were in the colonial age was at its peak. Then most of the development took place in England and Britain. So that was your 1845. And for India, the first official telegraph office was opened in Calcutta. And it has physical line laid between Diamond Harbour, that is your Calcutta Port, and till the Central Calcutta Telegraph Office. And that was way back in 1851. And in 1852, the first telegraph office in India that was opened at Calcutta. Then in 1865, ITU was established, and 20 European countries were part of International Telecom Union, ITU. Then in 1866, the first transatlantic cable was established between US to France. That was submarine cable, and it was a copper wired cables which were used for communication purpose, and that the communication was telegram only, telegraph. Then India got connected from London to Bombay through the same telegraph cable, and that was in 1870. That cable was laid from London till Bombay. So that the cable original photograph is there with me. I'll share with you in the coming slide. Then 1876, the telephone was made by Bell. So he invented telephone, and after that, the telephone communication started. So for India, the Telegraph Act was laid in 1885. And first manual exchange was established in Calcutta was in 1882. That was a telephone exchange. It was a manual telephone exchange and with 50 lines only. And that was established in Calcutta. That was in 1882. Then we move further. In 1885, now this is 1895. Indian side is J.C. Bose. He transmit wireless in lab. But unfortunately, the radio, the discovery of radio is not attributed to J.C. Bose. It is attributed to Marconi. And Marconi actually demonstrated after 4 years after J.C. Bose has demonstrated the radio in the lab. But everybody says that Marconi is he who discovered wireless telecommunication. But if we go by reality, it was a Bose who has discovered wireless communication. But Marconi demonstrated, and it is radio is attributed to Marconi only. And then in 1933, the Indian Wireless Act came. We were under British that time. Then after that, in the electronic switching, that is after discovery of transistors, the electronic switching came, and it was in 1995 when electronic switching came in the world. Then the further you can say development took place towards what we say satellites. And the first artificial satellite for long distance communication, we use satellites. So that's why the first artificial satellite that was put into the orbit by USSR, that was Sputnik, which was in 1957. And then in 1960, the first your STD, that is your subscriber track dialing, started in India between Kanpur and Lucknow. That was in 1960. 1974, first Indian artificial satellite, that is Aryabhat, was launched, but by a USSR rocket only. And and we'll see all more development of satellites once we talk about satellite communication. Then these are more recent. In 1979, the cellular technology came in Tokyo, that is Japan. That was the first to establish cell technology. Then in 1988, GSM came, that is Global System for Mobile, GSM, with 13 European countries. In 1989, the Telecom Commission was set up by Government of India. 1990, the WWW, that is World Wide Web, was proposed by Warner Lee, and HTML, and that is which later on become Internet, came into the purpose. Then in 1991, Internet came into the civil domain. Actually, Internet was developed previously for only our US Army domain. So it was only 91 when it came into the civil domain. And in 1992 onwards, the commercial impact of World Wide Web was felt when Internet came into full-fledged state. Then we see more recent developments, that is from 1994. For India, India developed the National Telecom Policy, that was in 1994. And private sector was asked to come into the telecom sector. And first phase of liberalization of mobile telephone services started. And 8 licenses were given to your mobile telephone services. So for cellular mobile telephone services, CMTs are cellular mobile telephone services, and 8 licenses were issued in 4 metro cities. That was in 1994. So we can say in 1994, the cell phone came to India. And then in 1995, the internet services were launched in India. And for internet services, the cell phone infrastructure had given easy access. Then in 1995, further 34 mobile licenses were awarded, and in 80 license area services. During this period, maximum of 2 licenses were granted to CMTs and each service area, and these licenses were called first and second cellular licenses. So that was till 1995. In 1997, TRARI was established, and that is Telecom Regulatory Authority of India. And now almost all the your regulatory work is done by TRAI. So even establishing how much your telecom should cost you and all those things are done by TRAI. That is your tribe. Then 1998, the first private landline service was started in India. Then 1999, the announcement of National Telecom Policy, it was revision actually. Then long distance telephoning opened up for competition, 1999. Then it was the first three pumps which came, that was from 1997 to 1999, that is Lucent, Motorola, and Texas Instruments opens up designs offices in India. Then Information Technology Ministry was set up with IT Bill, that was in 2000. Department of IT merged with Ministry of Communication, that was 2001. Then in WLL, that is wireless local loops, which made possible, which was the replacement to wired telephones. It came presence in India in 2002. And then VoIP, Voice over Internet Protocol, it was permitted in India in April 2002. So in 2003, government introduced UAS, that was Unified Access Services Licensing Regime, so where multiple services can be given to the same service provider. So we have both fixed and mobile services under the same licenses. Then 2010, the first time the spectrum was auctioned for 3G, and that was and BWA, that is 2100 megahertz, that was for 3G, and 2300 megahertz for broadband communication, the BBA, broadband applications. Then 2012, National Telecom Policy introduced unified licensing regime, and the spectrum licensing authority was given to the DOT, that is Department of Telecom. Previously, it was with the government. Now it is with the Telecom Department of Telecom. So, Department of Telecom had the got the authority. That was done in 2012, and that made licensing policies more transparent. In the 2012 to 2016, once licensing came to DOT, the different spectrums bands were licensed and they were given to different users. So 800 megahertz, 900 megahertz, 1800 megahertz, 2100 megahertz, 2300 megahertz, and 2500 megahertz, and that happened from 2012 to 2016. In 2018, Government of India changed the name of Telecom Communication to Digital Communication Commission. From Telecom Commission, it became Digital. So right now, it is Digital Communication Commission. And the National Digital, the total name is NDCP, that is National Digital Communication Policies, were seek to unlock the transformative power of digital communication networks and to achieve the goal of digital empowerment and improve well-being of the people of India. So that was the goal for National Digital Communication. And accordingly, the policies were made. So this was released 2018. So this was the first cable that I was talking about, which was laid between London to Bombay, and it was British India Submarine Telegraph Company. This was the company which laid this cable. So this is the cross section of the cable. So this was laid in 1870. So that was the first telegraph link that was established between London and Bombay. So now we talk about telecom infrastructure. So basically, there are two types of most used telecom medias. First one is guided and other is unguided. Guided is where we need to give some physical wire to guide the signal from source to destination. So guided is basically what we call wired telecom infrastructure. So the old infrastructure that we had was copper wires, where wires were connected from pole to pole, and it used to go from one place to another using copper wires. Then right now, at present, then there were telecom cables. In telecom cables, there were two types of cables. One was submarine cables, which were used between connectivity of two different continents or two different countries, which were separated by sea or ocean. And then we also had your wire cables, which were underground cables, but they did become very successful. But then came optical fibers or fiber optical cables. So the fiber optical cable right now, what we can say is the actual infrastructure that we have for telecom or the long haul communication, the real backbone right now, as well as in future, is going to be optical fibers. So the fiber optical is the most used guided medium for infrastructure purpose. Unguided, or what we say wireless. So wireless, the older was terrestrial radios, that is your basically AM FM radios that was used. Then the other wireless is satellite links, where you use communication satellites to establish the link between ground stations. And then interconnecting inside the cable, inside the country, as well as uplinking and downlinking, we use microwave links. And in microwave, we normally use LOS, that is line of sight communication. So we will see all these things one after another. So, so what is the most desired communication model? So this is the most desired communication model, that means what everybody desires to have. So actually, as a human being, we don't like foundations. That means we don't want any limitations. What we desire is we want information anytime, anywhere without limitation. Which means this anytime, anywhere without limitation is only possible if we have wireless access. So we want wireless access. So for accessing information, we need wireless. So right now, the most desired telecom model is where you have wireless access, where you can access any information from any time, from anywhere, without limitations. But to give you that access is not possible because the communication has to be a long distance communication. So the information has to come from somewhere. So the information that has to come through what we call as long-haul communication. Long-haul communication is communication network that handles communication traffic over long physical distances, such as nationwide or worldwide. So for long-haul communication, that means for worldwide communication or long-haul communication, we need wired infrastructure, or we need the backbone network. So backbone network need to be wired or satellite or whatever way it can be, but the access should be wireless. And that's why your cell phones have become most desired way of communication, because you carry it in your pocket, but what it accesses the long-haul communication, which so you have your modern telecom. So modern telecom provides wireless access of information globally using wired guided long-haul communication network. So this is the most modern way of communication, where our access is wireless, but the backbone is your backbone infrastructure is wired, and the wired infrastructure that we use here is mostly optical fibers. So this was the desire, what human desires. Now to fulfill this desire, yes, the time has come and it is more or less fulfilled. And so for long-haul communication, for the global long-haul communication, the two most used infrastructures are satellite communication and optical fiber networks. So we'll be talking about both of these infrastructures, satellite communication as well as optical fiber. So we start with the satellite communication. So first of all, as a question, what is a satellite? So satellite is a solid object which revolves around other body to the effect of gravitational force. One of the satellites that we have is Moon that we have, which is a natural satellite. But we also have artificial satellites. Artificial satellites are man-made objects which are placed into the orbit by human endeavor for some purpose. So these are artificial satellites. And in communication, we normally use artificial satellites. So in artificial satellites in communication, we normally use two types of satellites, is active satellites and passive satellites. Old were the passive satellites. All new satellites are active satellites. Active satellites and passive satellites are basically, passive satellites we can use even the natural, some natural as well as artificial satellites. Active satellites, these are objects in the space. So we can use those objects to get back the signal from the Earth by reflection. That is your passive satellite. And active satellites are satellites which are powered, which have, we normally power satellites by solar powers, and there are amplifiers in it. So we uplink the signal, satellite gets that signal, it amplifies the signals, and then it downlinks the signal back to the Earth. Now, the advantage of this is we can cover lot of distances. Like if, especially in the geostationary satellite scenario, we will, we with the single satellite, with just 3 satellites, we can cover the entire Earth. So just with 3 geostationary satellites, it's possible to cover the entire Earth. Because like just by height of antenna, it is not possible to cover the entire Earth. The reason is very obvious, because if you're on one hemisphere, the other people on the other hemisphere. So even how big antenna you make, you are actually making antenna in 2 different directions. So it's not possible by just height of antennas that we can have line of sight communication any because of the curvature of Earth. So satellites are needed. So we can see some. So satellite, the first satellite was by USSR, Sputnik 1. We already talked. It was in 1957. So this is the artificial satellite, which you can see, which is in its orbit. And from there, you can have the view of Earth. So satellite covers a very large portion of Earth, and that's why we can use satellite for communication. Then first Indian satellite was launched by USSR 1975, that is Aryabhat. We'll see all those things a little later. We'll see the Indian complete history of Indian satellites. Then these are the components. These are the outer components of a satellite. So normally satellites have solar panels, which are there to get energy from sun, convert it to electrical energy, then give it to the circuits, which are there inside the satellites. Then you have a solar arrays. Then there are these Zenith S-band, all these are inside, you have a battery. Then these are all antennas, and you have its own bus module. Then these are all others are antennas, which are part of the satellites for communicating signal from Earth. So you have SAR antennas, SAR antenna, tie-down antenna, X-band antennas, S-band antennas. These are different bands of, we'll talk about it in little later, the microwave bands. So these are microwave antennas, and this is placed into the orbit. So this is the components, these are the some of the components of satellites. These are outer components. The inner components of satellites, we have a command antenna, which is at the end. This is used for, if satellite drifts a little bit, we can bring it back to the, and also for the internal circuitry commands, which are given through this command antennas. Then you have communication antennas. The communication antenna, which I showed here, these are loop antennas. But not only loop antennas, nowadays it's possible even to use bigger, better antennas. So that is your communication antennas. Then you have solar cells. Then inside you have some batteries, because these batteries need to be charged, especially for ellipse type for satellite. When satellite is not receiving light from sun, those are called eclipse time for satellite. During that time, these batteries play an important role to keep the communication working or to keep the circuits inside powered. Then you have radio transmitters and receivers, which is used to give the signal and get the signal, the uplink and downlink. Uplinking means from Earth station to satellite is uplinking, and downlinking is from satellite to the ground station, that's downlink. Then it may have some auxiliary fuel, may be kept. That is, it is because sometimes there are small rockets which are attached to it, and this rocket fuel is kept for drifting the satellite. Satellite get little bit drifted from the orbit to bring it back the orbit. Then you have a thruster that is to just movement of the satellites. Then you have cameras. So these are the inner components of satellite. But for communication purpose, we normally use uplink antennas. That is from down from Earth, we uplink to the satellite, and then we downlink to the satellites. Then types of satellites, these are the uplinking, downlinking frequencies which are assigned to the satellite frequency bands. So you have L band, which is 1 to 2 gigahertz, then S band, 2 to 4 gigahertz, then C band, which is 4 to 8 gigahertz, which is used for television and other things. Then you have X band, which is 8 to 13 gigahertz, then KU band, is 13 to 18 gigahertz, and for your direct to home, that is dish and dish television, we use KU band, that is your DTH, direct to home services. These are the different bands of satellite which is used. Then types of satellites. Now, for communication purpose, we normally use only two types of satellites, that is LEO satellites and GEO satellites. These are type of orbits depending upon the altitude of satellite from the surface of Earth. So we have first orbit, which is called lower Earth orbit or LEO. Then you have medium Earth orbit or BEO, and you have geostationary Earth orbit or GEO. So it's basically, and because satellite has to remain in the orbit is because of its velocity. So at a different altitude, it has different velocities. So the nearer the satellite, faster it will be moving. So LEO satellites are lower Earth satellites, which are normally used for satellite telephony, as well as spying and other it has uses, but its area of coverage is small and has low lifespan. The reason is it's near to the Earth, which is 600 to 1,000 kilometers, and it has to move very fast. So it comes to the same place maybe once, 2 to 3 times a day at a time. So there is a satellite telephone which is iridium that was established, but it never become a success except for satellite telephones are normally used now also. It is possible to use, but it's very expensive. So because after when the cellular phone came into the purpose, came into the scenario, the satellite phones were never used. That is true. Satellite phones are still used by very rich people, by terrorists, and these are the people who are still using the satellite phones, but common man hardly uses satellite phone. So that was with the LEO. The technology here was very simple, where satellites were in sync with each other, and by using more than one satellite, you can cover the entire globe. That was the technology which was used for LEO satellites. But then we have medium Earth orbit. Now, medium Earth orbit satellites, this is elliptical, but these are hardly used for communication. That is, the MEO satellites are normally used for remote sensing and remote tracking. That is for what we normally use medium Earth orbit satellites. The most used satellites for communication purpose are geostationary satellites or geosatellite. This is only a single orbit, and which is exactly at 35,786 kilometers from the surface of Earth. From the surface of Earth, it is this. Now, in this orbit, the only advantage that is here, the orbital velocity of satellite is the same as the rotational velocity of Earth. So it is your satellite's orbital velocity, and because orbital velocity is needed to keep the satellite in the orbit. So that velocity and the revolution of Earth both are synchronized. So what happens is, since it is moving in sync with the Earth's rotation, this satellite looks stationary in the sky with respect to Earth. So it is possible to use with geostationary satellite what we call tuned antennas. We can use tuned antennas because once we tune the antennas to the satellite position will remain same. So on the Earth, you don't all the time have to change the antennas. So tuning of that means physical movement of antennas is not needed, because most of the time the satellite is stationary as with respect to the surface of Earth. So all the time the satellite is available at the top of you, wherever you have kept the satellite. So with geostationary satellites, with just 3 geostationary satellites, so it can cover 120 degree of the angle, that is your solid angle of 120 degree. That much portion of Earth you can cover. 120 degree means total 360. So with 3 satellites, it's possible to cover the entire Earth. So geostationary satellites, they are the most commonly used satellites for communication purpose. The single satellites can cover 40% of the Earth. So with 3 satellites, we can cover entire 100%. So because of its very large coverage, so the geostationary satellite will always be used as a reflector. We send a signal to the satellite and then downlink at some other place on the Earth. But the distance covered by it will be just by using a single satellite, we can communicate from India to say US. So that way we can use geostationary satellites. So because of this area being very large, coverage area, so it is used. Then we can say the Indian satellite program. So our program started in 1963 when India established Bilaspur rocket launching station, that is later TEL intervention program. So that was in 1963, where our satellite program got started. Then, but we can say, but we then in 1968, the TEL was dedicated to UN. In 1969 was the birth year of ISRO. That is, Indian Space Research Organization was established, and it was established under your atomic energy, under Department of Atomic Energy. So 1969, ISRO came into picture. 1972, the Department of Space was established, and India started making satellites. So the first Indian-made satellite, that was Aryabhat, which was launched not by India, but by USSR that time, or Russia at present. So in 1975, or 19th April 1975, from Kapustin Yar in USSR, that time the Aryabhat was launched, and the Aryabhat was not a communication satellite. It was a radio astronomy and remote sensing satellite. So that was the first Indian-made satellite, which was launched in 1975. But again, not by, but right now we have capability to launch even geostationary satellites. So we'll see how. Then these were some of the programs which started with with satellite projects. So satellite telecom experiment projects and satellite instruction TV experiment. So these were for first program was used for adult education as well as for education, other education, and the satellite telecom experiment project, that is STEP, was used for communication. It has communication component, so that is with inset. We'll see all those things. Then in 1981, the first development model of satellite launch vehicle SLV was launched with RSD-1 satellite. That is your satellite launch vehicle SLV-3 that were launched. Some of the SLVs got crashed, but 3 was successful. 1 and 2 was lost. Then we have your first Asian passenger payload experiment, Apple. That is GSO communication satellite. That was Indian satellite, was lost from ESA rocket in Prof, French Guiana. That was 1981. So we'll see more details now. So this was that is your Indian National Satellite System inside. Hello. Am I audible? Hello. Your principal there? Hello?
Yes, sir. Yes, sir. We can listen to you very clearly, sir. Thank you, sir.
Am I audible?
Yes, sir.
Yes, sir. You are audible, sir.
Yes. Okay, okay, thank you. There was some disturbance, so I stopped. Anyway, set. So this is one of the largest domestic communication satellite system in Asia Pacific. Even right now, we can say even worldwide, this communication system, the number of satellites that we have is very large. And most of them we are still using. So INSECT 1A failed in the orbit. That was in 10. It was launched on 10/4/1982, and it was for communication, but it was a failure. Then INSECT 1B successfully launched, and it was used, and some portion is still being used. That is your 1983. Then INSECT 1C and 1D. So INSECT 1C was launched on 1988, and 1D was launched in 1990. But your 1C was a partial failure, not the full failure, but it was a partial failure, but 1D was full successful. Then 2A was launched, 2B was launched, 2C was launched, 2D failed in the orbit, but still others were success. Then INSET 3B was a success, and it was launched in year 2000, that is 22/3. The first and this 2A and this 2 series, they were actually multi-purpose satellites, which means it has capability not only for communication, but for other purposes also. That is your remote sensing and other purposes. Then our one of the biggest achievement in a very recent was Mars orbital mission, or Mangalyaan, which was a big achievement of ISRO in 2013, where we were able to place a spacecraft of 1,337 kg, and that too in the orbit of Mars. So that was important. So this was a Mars orbital mission. So it is a huge satellite, what we can say, achievement of Indian satellites. And by this, we have proved to the world that we can not only place any satellite on any orbit around the Earth, but we can also place satellites around other planets if we wish to do so. So this was a big success of ISRO. That was one of the biggest achievements. Then these are the specifications for INSET 2C, which is multi-purpose communication satellites. So it is used for communication, for meteorology, which is your basically weather forecasting, and for satellite-based research and SCQs. So the weight was 1,906 kgs, and on board it has 1 kilowatt approximate onboard power. It is for communication. It has C and S band antennas. Then it has all the 3 axis stabilization. That is your azimuth axis stabilization wheel. Then it has other things. So these are all available, which you can see. And for any satellite, all these specifications are available from ISRO's official website. So anyone interested in seeing these specifications can very well visit ISRO's official website and see because so in our in communication satellites we have from INSET now we have GSET. INSET was Indian satellite system. Then we have a GSET, which is global satellite system. Joins the consolidation of INSET. So we have INSET 3C, 3, 4A, 4B, 4CR. Then we have GSETs 6, 7, 8, 9, 10, 11. The number system is like this, and 18. So these are the global satellites that are Indian made satellites. INSET systems inside systems with more than 200 transponder in C extended C and KU bands provide services for telecommunication, television broadcasting, satellites news gathering, societal application, weather forecasting, disaster warning, and search and research rescue operation. So this is how we can use our satellites. And very recently, we have now even India is having our own very good camera carrying satellites, which can see almost is possible to see say a vehicle or a person moving on our surface, so which can easily be used, especially for our border borders. It can be used for what we actually call for security purpose, and so these satellites can be used for that purpose also. So these are our recently launched satellites. So GSAT-30, it was launched on 17/1/2020, this year only, and but it was launched by not by our own vehicle, but we have used Arena rocket from French Guiana in South America. So most of the satellites were launched by them, but made in India. Our own launched satellite was GSAT-7A. It was launched on 19/12/2018, and for communication purpose, and it was used using GSLV F11. And from Sriharikota, it was launched. So from satellite point of view, India has the capabilities. We can launch any, because if these are geostationary satellites. When we talk about GSAT, they are geostationary satellites, communication satellites. So if you are able to send a satellite to the geostationary orbit, we can send to any other orbit. So that's not a problem. So India has the full capabilities to send a satellite of its own up to geostationary. Not only geostationary, we can send to the other planets' orbit also if we wish so. So that is what technology at present we have with satellites or communication satellites. Then the next thing that is used for long-haul communication, that is optical fiber cables. So because satellites we have already seen, the infrastructure that India has and the capabilities India has. So we'll talk about long-haul communication networks, which are here for the communication purpose, and the optical cables. So actually, optical cables, so this is a picture of an optical cable. So we can see different parts of optical cable. We have armor protection, then we have insulation jacket, then you have a copper sleeve, then you have strength wires, then unit fiber structures, and after that we have optical fibers. Now optical fibers are actually glass fibers. So in glass fibers, by using total internal reflection, we can send optical information from one place to another. But only problem that optical fiber that has, since it is a glass fiber, it is very feeble. So being very feeble, that's why it needs so much of other support, so much of support from other materials to use these cables. And but the capability of carrying information that optical fiber has right now, theoretically, we can say it has infinite bandwidth. Theoretically, infinite bandwidth basically means that does not mean that it has infinite. Actually, it has infinite bandwidth. Actually, right now we don't have switching that can take place in the optical band. The switching that we have is only in few gigahertz. We can only switch in few 100 gigahertz. Whereas the optical band, the bandwidth that the optical light, it has frequency in terahertz. So we don't have terahertz switching. So right now the problem is we don't have switching technologies that can switch at the speed at which the signal can actually pass through the optical fiber. So the bottleneck is at the technologies which are switching technology which connects the optical fiber. So that's why we can say the bandwidth that the optical fiber has is infinite. But is only what we can say is we don't have right now the infrastructure which can handle the switching that is possible with an optical fiber. So that's the thing. But the other way to say is it has very large bandwidth. So since it has very large bandwidth, a small, very thin wire can carry a lot of information without problem from one place to another. So it has become the most used way for communication or for the long haul communication. So the development of technologies increase the demand and compel the use to use optical cables, backbone for data network, broadcasters for wireless communication. And optical fiber is a hair-thin cylindrical fiber of glass or any transparent dielectric. So this is your, since it's, so the mechanical strength is very low. So since mechanical strength is very low, it needs to be protected with lot of enforcement. So that's why in a cable, you have a lot of enforcement to protect these glass fibers. But these glass fibers themselves can carry a very large information. So the function is to guide visible and infrared light over long distance. So that is the basic purpose. So this is about a long fiber. So we can see this. So first of all, why OFC? So the reason is because of its advantage. So before optical fiber cables, OFC, the copper cables were used, which I already told you. I've showed you that undersea cable. And this optical cable, so advantage it has over the copper cables. The transmission bandwidth of fiber optical cable is much higher than copper cables. So this is its one of the most important advantage, that the transmission bandwidth of optical fiber cable is much higher as compared to cable. So with a single hair thin wire, we can carry terahertz, or we can carry the terabits of information without problem from one place to another. The power loss is very low because it uses optical light. So light, if it goes through a bounded surface, it doesn't lose. We don't lose much. So since power loss is very low, so it is very helpful for long distance transmission. Then it gives a very high security, except for it is very feeble. But once it is used, then you cannot tap into it. And even from outside, any electromagnetic interference will not interfere with the information passing through the optical fiber. So it gives you a very high security. Mechanically, we break the cable, we lose all the data. So that is there. But we cannot intrude into the system. So that's why we say high security. But only problem is it is very feeble, so it has to be kept. That's why we use either underground cables or we use undersea cables for optical the OFCs. Then it is immune to electromagnetic interferences and electrical noises. The capacity of this cable is much higher than copper wire that we already talked. And cost and space occupied by office is also very less as compared to copper cable. So even its cost is much lesser, and the space used, because it uses hair thin glasses. So that is that thin copper wire cannot carry anything. But here is possible. Since these cables are dielectric, those spark hertz hazards are present. Since it is a plastic or is a insulator, so you don't get shocks from these cables. Then no sparking, nothing. then more corrosion resistant. It is less than the copper cable. They are bent easily and are flexible. Then fiber optic cables last longer than cable. The lifespan is much larger than the copper cables. So these are the advantages of OFC over traditional copper cables. Then history of optical fiber development in India. So actually, in 1956, Raghuwanshi Singh company introduced fiber optic cable in India, and he's also known as the father of fiber optics. In the beginning of 20th century, the British government established the communication link using coaxial cables. That was what we talked about in 1870. Then for India to join optical cable club, it's quite recent. That was only in when Government of India approved National Optical Fiber Network NOF initiative, and this was done by right now it is called BharatNet. So we'll be talking about it in details in the coming slides. To connect, we actually BharatNet, that is your BharatNet, which is decided, and what we are thinking is to connect each and every gram panchayat of the country using optical fibers. So this is desired. So it's already first phase is completed for BharatNet, and the second phase. So we will be seeing that progress, how it is being done. So the objective is to connect all 2,500, that is your 250,000 gram panchayats of the country, covering nearly your 625,000 villages of the entire country, and using optical fiber network. To achieve this, Bharat Broadband Network was incorporated in February 2012 under the Company Act, and 16 states, union territories signed MOU with it, and 140,727 gram panchayats had facilities for the fiber networks. So this we can see later. So this is that is in India. So 13 to 14% of Indian nearly 4 lakhs telecom towers are connected through optical fibers. Only 13 to 14% of Indian right now. And effective data networks of 4th generation technology requires 90 to 95% optical fibers for telecom towers. So with coming technologies, we need to connect more, and this was the reason for the Indian optical fiber OFC's market is around $1 in 2019, and it is projected to be 2.1 billion by 2024. So moreover, growing demand of OFCs from IT telecom sector, rising for the mobile devices, increasing adoption, that is your fiber to home connectivity, and surging number of data centers is further anticipated. So this is because there is a very large demand for OFCs. So this was the step which was taken. So Government of India has approved the setting up of National Optical Fiber, or NOFN, that was on 25/10/211 to provide connectivity to 2,000 towers 2,550,000 gram panchayats of the country under UP. So this actually NOFN it came under UPA. That was under UPA previous government. And this was needed to ensure the broadband connectivity with adequate bandwidth for providing and extending every gram panchayat. So the World Bank study has estimated 10% increase in the broadband connectivity by 1.8 gross domestic product. So broadband penetration in India is at present less than 2%. So this is was the thing. And to achieve this, the BharatNet was established. So actually, BharatNet was just National Optical Fiber Network, or NOFN. It was renamed by NDA. It was UPA government's project, which was optical fiber NOFN, and it was renamed as BharatNet. And this BharatNet is actually the you can say the rebirth of National Optical Fiber Networks, and agency called Bharat Broadband Network Limited, or BBNL, was established to implement BharatNet. So BharatNet was to be implemented by BBNL. So BBNL was set up by government under the administrative ministry in telecom for the operation of BharatNet. So BharatNet is actually a new name given to the old National Optical Fiber Network. So then BBNL is working, and we can get the daily whatever they have achieved every day, they upload. So this slide was made on 2nd of October. That's why the latest BharatNet, how much it has achieved, we can see that, which is shown in the coming slide only. So current status of BharatNet is, it was implemented in 2 phases. First phase was to give 1 lakh gram panchayats, so that is completed. And the second phase is still going on, and it is being implemented by BSNL, RailTel, PGCL, CSC, and other operators. So existing fiber of BSNL, that is your block 2 gram panchayats, used to lay and connect RFC under the regime. So this is your BharatNet. It is mostly working with the overground networks. So this is your different states. They have different things. So number of gram panchayats covered so far. So this is in 2020, October 2020, the latest the status of BharatNet. The number of gram panchayats covered is 65,590 in these states. Then similarly for private, this is state-led model. So Chhattisgarh also is working with the state-led model for BharatNet. So these are total number of covered. Then number of total number. This is how much is actually this should have covered. So there is shortfall of around 20,000 gram panchayats. So this is being done. So we can say from total, this many are already covered, and these are where the work is being, which is supposed to be covered. So the difference of it will give us those gram panchayats which are not yet covered. So these are your this is the status for BharatNet on October 2020 in the second phase implementation. So this phase is still going on, and by 2024 they may cover the second phase that is projected. So this is your current status on 2nd October 2020. So total OFC laid length is 4,59,124 kilometers. Number of gram panchayats with lead OFCs covered is 1,57,624 gram panchayats, and number of gram panchayats made service ready. Service ready means these are just covered, and these are the gram panchayats which are made service ready. That means they have on fiber and satellite. That means they are being used are 1,45,545. So these many gram panchayats are already connected, and connect your 1,57,000 are already connected, and these are made operational. So 1,45,000 out of 1,57,000 connected are operational, and this is status on 2nd October 2020. So one thing with good with this project is it's a very transparent project. So almost every day you can see how many new gram panchayats might be getting connected. So they are running more or less in time, and their target is by 2024 they should be able to achieve it. So then submarine fiber link in India. Now submarine, this is an photograph of a submarine fiber cable. So submarine fiber cables are the cables that are laid under water. So here from Indian, because India happens to be more of a land country, we don't have most of the countries on land. So the optical fibers that we were using other countries under submarine fibers, and we were giving what we have hired the bandwidth from them, and we were using those fibers. So right now, we have only one submarine fiber link, which India has made by itself, and which is being used, and it is very recently it was inaugurated. So we will see about status of submarine fiber links in India. The foundation stone for first Indian submarine OFC project was laid by Prime Minister Modi on December 30, 2018. And 10th August 2020, it was inaugurated, the submarine optical fiber, which was capable of connecting Chennai and Andaman and Nicobar through video conference. So it was only on 10th August 2020, very recently, this was the inauguration of submarine optical link was taken place. This cable is 2,300 kilometers under the sea. It can give speed of internet speed. It can provide up to 400 gigabits per second, very high speed internet for Port Blair, and 200 Gbps to the other islands. So very high speed internet through this fiber is possible. The entire work of laying undersea cable was done by BSNL, achievement, and they did it in less than 24 months. So 2 years they were able to do it. The optical fiber cable is supposed to connect other islands. There's Swarajdeep, Long Island, these are other Andaman Nicobar Islands through with Nicobar and Greater Nicobar. So we can see the pictorial look of this. So this is from Chennai, and these are Andaman Nicobar. So this is it is laid from Chennai till Andaman Nicobar, and it is proposed to connect it further from Calcutta. But that is just a proposal right now. Right now we have only this link, and then there are other link which is connecting other part of other islands of Andaman Nicobar with the cable. So these are the different other islands which are connected using a submarine fiber link. So So this is basically the status of submarine fiber link in India. Then now as I told you, the infrastructure side we want wired or central link. Then for wireless access network we need access should be wireless. So the access part of the wireless infrastructure, that is we can talk about the wireless access networks. The cellular network or radio network distributed over land areas are called cells. And this I can explain to you more with the pictorial. You can see this is a cellular network or wireless access. So basically, these are the mobile phones that we have, and then you have BTS, you have BSCs, you have MSCs, and you have internet, which is data networks. Base, you have base transmission station, which is the nearest antenna to which your mobile get connected. That's called BTS. And your main switching center is MCs, and your base switching center and main switching center. So how the cellular network works is you have your mobile. The mobile is provided with a SIM or subscriber identity module. That SIM has the your service provider. The service provider provides you a link to connect to the BTS. So we connect ourselves to the BTS, and it is a two-way link where one channel is attributed for your incoming signal and other is attributed to your outgoing signal. So it's a two-way link. So two channels are given to your system, and you get connected to the nearest BTS. And this is the reason why nowadays it is possible that whenever you are carrying your mobile, the location where you are is always there in the mobile, because you are always signing into the nearest BTS or nearest antennas that you see around. And once you get signed into it, then you are only communicating from your mobile to that antenna. And the rest communication is taken care with the connection that we have. So the long haul connection here, so all these connections that you are seeing here, they may be optical fibers. But your connectivity to the station will be wireless. So you access through the BTS. Once you access, you dial a number. There will be another person somewhere else in some other different cellular network. He will be connecting through his own BTS. He will get the ring, and then you talk to each other. So the actual communication that is taking place is from your mobile to the base station and back to your mobile, and you're getting back signal from the base station. So your wireless connection is only between you and BTS. The rest of the connection is through optical fibers, maybe through satellites, maybe through other, and then it reaches from one place to another. So this is your cell. Now this cell phones. So these are your different
Excuse me, sir.
generations of. Hello.
Excuse me, sir.
Yes.
Sir, sorry to interrupt you. Sir, we are getting short of time actually. From 11 o'clock, we have some next section also. So.
Okay, I'll finish it fast at 6. I'll just, at this slide only, I'll finish it up.
Okay, sir. Thank you.
Okay, thank you, sir.
Okay, so these are the generations of mobile technologies that we have. We have 1G, 2G, 3G, 4G, 5G, and then 6G. So 1G, it was from 1970 to 1980. That was 1G. But 1G never came to India. So in India, we never had 1G mobile as such. Then from 80 to 90 was 2G, which in India we joined in 90s. So that time 2G came to India. Then from 19 to 2000, the 3G came. 3G came in 1990. And then you have that time. Then we have 4G. 4G's launch was supposed to be in in 2010 around. So the 4G, but it became a bit late. Then 5G was 2015. Actually, the 5G got still it was launch was supposed to be 2020 this year only, but because of COVID and other things, this has gone back. Although there are technologies already available, especially UAE, which is Chinese company, which are having these technologies from 18 itself. 2018 only they had 5G technologies, but because of US and China thing, that has never came into actual thing. So how they are different is by their speeds. We can say 1G provided only 2.4 kbps, 2G provided 64 kbps, 3G provided 2 mbps, and 4G was 200 mbps to 1 gbps, and 5G is greater than that. The other thing is their technologies. So your 1G was analog cellular mobile, 2G was digital cellular mobile, 3G was broadband and CDMA IP based, 4G was unified IP, 5G is WW, that is your totally IP based, and 6G will be with satellite and IP based. Then the standards, EBI AMPS, then GSM, then CDMA 2000, that was for 3G, and LTE for 4G. CDMA or FDMA is for 5G, and IPv6. So that is for 5G. As 6G is 6G is still in development phase. So this is about generations of technologies. Then these are you can go through it. First D, second D, 3G, 4G. This is given. Now access techniques. This was more of a technical, which I wanted to give you, but already we don't have time, so I'll just say FDM. That is your. You can just go through the slides. Frequency division multiple access, time division multiple access, code division multiple access, orthogonal frequency division multiple access. Then this is the way orthogonal frequency division multiple access works. It just this is more for a communication person. So anyone who is interested can see these things. Then this I wanted to give was frequency reuse, which made possible for cellular phones to come in such a large way. But anyway, you can just see things. So this is the future technologies. That is your 5G. So 5G provides larger broadcasting in gigabits. 5G terminals have software-defined radios. 5G uses different modulation techniques and error control techniques. 5G provides hundreds of channels without streaming. 5G offers transporter class gateways. And so these are the advantages that 5G is having. Yes, but 5G and 6G, these are future technologies. 5G is not yet fully launched. In 6G is even still in future. We can have 6G. The only advantage with 6G is you can have high-speed streaming in your mobile network itself, which means you can watch a cricket match on RAN with 6G technology. Then these are the references. And thank you. And if you have any questions.
Thank you, sir.
If you have any
Okay, thank you so much, sir. For the concise, very important. So we are running, but we have still 5 minutes for discussion session. So Gurdeep Singh Bagga sir, you want to ask something?
Hello. Am I audible, sir?
Gurdeep.
Yes, sir. Hello. Am I audible?
Yes, sir, you are audible. You may ask a question.
Sir, thank you very much for this informative lecture on communication technologies. I wish to ask one question. Although you have covered various aspects which should be considered for understanding the efficiency of telecommunication infrastructure, what maybe some other aspects which we need to consider, like instead of connectivity and like data speed and technological facilities, what should be other aspects we should consider for getting the efficiency of telecommunication infrastructure?
Just a second.
So should I say it again?
Yeah. Please put it.
Sir, what should be, what are the aspects which we should consider for getting, for estimating the efficiency of telecommunication in a city or district?
Actually, when it comes to okay, I'll just remove it. I got